Thank you very much for having me, and thank you very much for organizing this last session. It was nice to follow the RQI Online throughout. It's nice to see the whole community, even though we cannot always meet. I prefer meeting in person, but it's nice that we have this thing online. Today I'm going to tell you about work that we are doing at the moment at Laboratoire Casler Bruxelles. It's experimental work in collaboration with theorists at Louisiana State University in the group of Ivan Agulo. And then the main person who is cracking on the numbers is Adria Delhomme, who is a postdoc. Whereas in the Laboratoire Casler Bruxelles, I work on the experiments with PhD students Kevin Falk and Kilian Guerrero. The topic of today's talk is really to tell you about superradiance, and I thought I could give a brief introduction on what I mean by superradiance very specifically. And this is all summed up in this picture that's on the top right of the screen, where we see that we have a potential with some maximum somewhere. It's a spatially dependent potential, but it's independent in time, so it's a completely stationary process that we are looking into. And we imagine that we have wave packets that can scatter on this potential, so they can be coming from the left or from the right. They are those red wave packets, and we wonder what's happening to the amplitude of the wave packets that would be reflected or transmitted, and these would be the blue ones. And usually when we do that, we write a Schrödinger equation, and then the quantity that is conserved during this scattering process is the probability. And the fact that the probability is conserved tells us that the modulus squared of the transmission and reflection coefficients add up to give 1. If, however, instead of a Schrödinger equation, we write something for a bosonic field theory, like a Klein-Gordon equation in Minkowski spacetime, or in Schwarzschild spacetime, or in a Kerr spacetime, then it's not the probability that is conserved, instead it's the charge. And the charge is a bit more special. It involves the special derivative of it involves the special derivative of the temporal derivative of the field, as well as the field itself, or rather the conjugate momentum of the field and the field itself. And because this is the conserved quantity and it can be negative, then it's really the modulus of the squared modulus of the transmission and reflection coefficients that adds up to 1. And we see in this equation at the bottom right of the screen that we can have conditions where t squared is greater than 1, provided that r squared exceeds 1 as well. In which case we can have really amplified reflection at the cost of having some transmitted light into a negative norm mode. And that's really what the Noether charge tells us. It tells us that as soon as we have negative norm modes that are available in the system and we have a way to scatter energy into them, then we can have amplification of energy when we have scattering of a wave packet. And that's encrypted in this B matrix, which is a matrix of complex coefficients. And if that matrix is not unitary, then we have amplification. And very generally speaking, this amplification is superradiant scattering. So one very famous example of superradiance scattering is rotational superradiance, as described by Zeldovich for a rotating cylinder, and that also exists in black holes. It's connected somehow to the Penrose effect. And that's what I want to look into today. I want to look into rotational superradiance in the laboratory. So I want to run an experiment where we see this effect. And the way we set up this experiment is that we use the methods of analog gravity, where we have a fluid with a certain velocity that's proportional to the gradient of its phase, the spatial gradient of the phase, and a speed of sound. We look at the acoustic field in that fluid. And the wave equation for the acoustic field in that fluid has this complicated shape that's in the center box, but it can be very easily written out in a simpler form by using the covariance notation and writing out a metric tensor whose components depend on the relative speed of sound and of the fluid in the experiment. And so if we have a flow that is inhomogeneous, such that somewhere we have the speed of the fluid that exceeds the speed of sound, then we will have some scattering that will occur in a purely stationary time-independent space-time. And the acoustic field then plays the role of the scalar field. It can be even a massive scalar field. That's what we have in our case. on a curved space-time. And this was all formalized by Unruh and Visser later on, and is the basis of analog gravity. So how does this work? Really, in the experiment, we take our metric tensor and we can have various scenarios. So the very famous scenario is you have a fluid that's just propagating in one dimension. In space, it goes from sub to supersonic. At the point at which the flow velocity of the fluid exceeds the speed of sound, we have an acoustic horizon. If we generalize this to two dimensions with rotation, then we have an azimuthal velocity as well as a radial velocity. Where the radial velocity exceeds the speed of sound, sound waves are trapped. We have a trapped surface that's an acoustic horizon. A bit further out from that surface, where the total velocity of the fluid exceeds the speed of sound, we have a static surface, and that's an ergosurface. And that's the surface that's of interest to us today. In the geometry that I'm going to show today, we have purely rotating velocity and no radial velocity at all. So we form an ergosurface and no horizon. And I'll explain later why this is super interesting to us. So the way we do the experiment is with these microcavity exciton polaritons, or polaritons really, which I'm not going to explain the physics of in depth today, but they are essentially photons that come from a laser that are dressed with material excitations that live in a plane. So it's a purely planar geometry. The way we dress the photons with excitations is that we confine the photons in a microcavity, a Fabry-Perot cavity. They interact in that cavity with the semiconductor electrons that are those excitons, and they found and they form bound states, those excitons, that strong couple to the photons. And via strong coupling to the photons, the cavity photons that already have a mass from confinement, an effective mass, acquire also the ability to interact non-linearly. So in the plane of our microcavity, the polaritons that are the result of the strong coupling of the photons with the excitons are bosonic particles that are able to interact with one another via some non-linearity of type K3. And their dynamics in the plane is described by the Gross-Pitarevsky equation. It's a type of nonlinear Schrödinger equation that's in the bottom box. It's got a term for the kinetic energy. We see that the kinetic energy of the fluid, the ensemble, comes from the mass from confinement of the photons, whereas the nonlinear interactions are all in Gn, and G is the interaction constant of the electrons. It's the contact interaction of the electrons. We also have, of course, the fact that we send photons in the system. That's our pump term, and at some point, the mirrors being imperfect, the photons exit the system. That's our gamma term. Those are the losses. So we have those bosons that have a limited lifetime. It's of the order of 10 picoseconds in the experiment. It's going to come back later, this 10 picosecond number. So if you want, I send photons on the sample. The photons interact with the electrons. They form those excitons. They strong couple to the excitons, and together they form those polaritons. They live their life described by the Gross-Pitarevsky equation. They de-excite, and the photons come out. And I observe those photons in the detection. I observe the photons, and by measuring the intensity of photons that I get, I have a relationship to the density of polaritons in the cavity. By measuring their phase, by interferometry, I have access to the phase of the polariton field. So I can do in situ measurements that are totally non-destructive, just thanks to the driven dissipative dynamics of my system. And that's incredible because I can also shape the beam that I send. And here we have the results of the experiment that I'm going to come back to later. But I can form a vortex of light that creates a vortex of polaritons. And in that vortex, I can have an ergosurface, and I can study rotational superradiance in the experiment. So the general idea here is to create a vortex, so that's a purely rotating system, or a maelstrom, that's a rotating system with some radial velocity. In our case, we have a vortex. And in the experiment, what we would want to do is to look at what happens, what's the fate of an excitation that would scatter on the ergosurface. I can send a probe to observe the amplification, or I can let the quantum vacuum scatter at the surface. The two work in the experiment. And then what I can do is, because I have access to the entire field, to commuting observables, I can measure quantum correlations across the ergosurface. I can see whether there is entanglement that's generated by the process, and I can even see, say, if I add now a horizon, I can see how this perturbs the entanglement created at the ergosurface and so on. So all this builds up on work that was done in the group of Silke-Weinfurtner in Nottingham, where they observed rotational superradiance in a classical fluid. In our case, the fluid is quantum. And they observed some other phenomena that are linked to those vortices, such as the ring down and also some sort of like back reaction. We are first and foremost interested in rotational superradiance in the experiment. So the experiment looks like this. I have a laser, that's my TISA, titanium sapphire. It's sent towards the sample in the cryostat. And on the way, I pick up some of it to make a phase reference for my interferometry to measure the phase. But I also have the light of the laser scatter on a spatial light modulator, this SLM, spatial light modulator. It's a screen of liquid crystals that I can orientate the way I want to imprint a phase on the light beam. So I can that way create my vortex. The two telescopes that are the pairs of lenses that are highlighted in green image the plane of the spatial light modulator in the plane of the cavity. So I have the phase of the spatial light modulator directly imprinted on the plane of the microcavity. That's my optical control. And then the light comes out and I observe it in real space where I do the interference and also with a spectrometer to observe the spectrum. So let's look a bit at the light vortex before we create polaritons. So I create an image on the plane of the spatial light modulator, and via and that phase is just this function here, C over R minus D over R, and we can see how it changes as a function of the C and D parameters. So, for example, the C is the circulation. So it's whether I have convergence of my beam or not, whereas D is the number of phase jumps that I will have. If you want, it's how many. Sorry, it's the other way around. D is the drain and C is the circulation. So C is how many phase jumps I will have, and D is the drain. And we see that as we increase D, the phase jumps, they become more and more curved. That's the signature of a drain. But I can also create beams in which there is no drain at all, D equals 0, and there we see that I can get a number of phase jumps, and these phase jumps will create a circulation that will create a purely azimuthal velocity. So now I send this light vortex in the microcavity, it interacts with the electrons, creates the excitons to which it strong couples, creates the polaritons, and I measure the light that comes out of the cavity, and this is an experimental result now. So on the left, we have the intensity of the light that comes out of the cavity. On the right, we have the phase. The intensity, as I said earlier, is directly connected to the density of polaritons in the plane of the microcavity, and we see that it assumes an annular shape. That's typical of Laguerre-Gauss beams. So that's a proof that we have created a vortex. And indeed, if we look at the phase, we see that we have a number of jumps in the phase. Here, I think 15. So we have 15 jumps in the phase. Of course, in fact, there is unit circulation. It's just that I have 12 quantized vortices at the center of my vortex. 15 quantized vortices at the center of my vortex. So we also see that the phase jumps, they are relatively straight. There is not much curvature to them, which seems to indicate that there is very little, if not at all, radial velocity. And indeed, if I do the analysis of that mean field data, I obtain the speed of sound via the square root of the density. That gives me the red curve on the right-hand side. That's decreasing from large radii to short radii. Whereas the radial velocity in green is on average 0 and very close to 0 everywhere, while the azimuthal velocity, which is the total velocity because the radial velocity is 0, has a 1 over r behavior. It grows as 1 over r from large to short radii. At some point, this azimuthal total velocity crosses the speed of sound, and by definition, that's where I have an ergosurface. So experimentally here, I am showing you a stationary state of a quantum fluid where we have an ergosurface. And we can ask ourselves, okay, so what do the modes of the acoustic field look like in this situation? So we can resolve the Bogoliubov dispersion relation here in calculations, soon in experiments. Outside of the ergosurface, where the flow velocity is lower than the speed of sound, we see that we have a black branch at positive frequencies and a red branch at negative frequencies. On the right-hand side, I write the Noether norm. I can tell you the black curve is positive norm modes, the red curve is negative norm modes. If now the flow goes supersonic, we are inside the ergosurface in the ergoregion. The negative norm modes are pulled by the Doppler effect. They are pulled to positive frequencies. So we have negative energy modes that are available, meaning that we can do superradiance scattering, right? This is a stationary system. We are in the stationary state. We have positive energy modes outside of the ergosurface, negative energy modes inside of the ergosurface. They share a common frequency. We can have superradiance scattering. And that's very nice. I mean, that's the experiment we want to run. But here, we have to ask ourselves the question, how is it possible that this is stable? I mean, if we think about it, there are always quantum vacuum fluctuations in the system. And I'm telling you that I can have superradiance scattering, but that there is no horizon. So there is no one-dimensional surface or two-dimensional surface that's going to take the negative energy modes out of the system. So here is how, with this quantum fluid of light, we can create a stable ergosurface without a horizon. So with a new dissipation mechanism. If you want, the group velocities that we are talking about, they are roughly the speed of sound. They are of the order of 1 micrometer per picosecond. That's the red curve on the top right. Whereas the lifetime is of the order of 10 to 15 picoseconds. What this means is that the mean free path of excitations in the system, be they Bogoliubov excitations or quantized vortices, is of the order of 15 micrometers. And what we see is that the density, which is proportional to the square of the speed of sound, decreases very fast inside the ergosurface. In fact, at about 15 micrometers radius, the density is of the speed of sound is of the order of 0.4. That's a very small density where we don't have nonlinear interactions anymore. Everything that is at red eye below 15 micrometers, in fact, has no physical meaning whatsoever. It's just noise in the data. So here in this experiment, if you want, sort of like 15 micrometers inside the ergosurface, we reach a point at which there is no more density, so at which there is no more Bogoliubov excitations, no more acoustic field. And so the negative energy waves disappear. They are taken out of the system by the intrinsic dissipation of the fluid. We have this microcavity, these intrinsic driven dissipative dynamics that allow us to pin the phase of the entire fluid with the pump and to ensure that it remains pinned and to reach a stationary state just because we have dissipation. So that's how this works. Now in calculations, Adrien Delhomme, he calculated that if we look at the vacuum fluctuations that scatter at the ergosurface and we add some realistic amount of thermal noise in the system, we have thermal noise in our system, of course, like in all experimental systems, we can still get some degree of entanglement that's quantified by the logarithmic negativity, here shown as a function of frequency. So we can still see some entanglement. So that's very nice. That's really the experiment that we want to run now that we have this stable ergosurface. We want to look on either side of the ergosurface, measure phase and intensity correlations and anti-correlations or other commuting quadratures. And we want to see entanglement that will be generated by the scattering of vacuum fluctuations on the ergosurface. Okay, so I think I've reached the end of my talk and the end of my time today with you. I've told you how we can run experiments with polaritons, those bosonic quasi-particles with a limited lifetime, and how their limited lifetime allows us to create stable ergosurfaces. I've shown you experimental data on that, which is very nice for us. You can find the experimental data in this archive paper that came out in October. Hopefully soon it will be published as well. And I've also shown you some preliminary results of calculations where we have looked at the logarithmic negativity. So it tells us that we can see entanglement in the system even though we have some finite temperature. We have ideas of how to increase the degree of entanglement in case the temperature is higher than what we estimate. So this is a very promising system here to look at superradiance without interactions with the horizon, but then we can switch on the horizon, we can increase the drain in our system all optically, and then we can look at the interplay between Hawking radiation and superradiance and see how this modifies entanglement, which happens in all black holes, but we cannot really see that there. So I think these experiments in that sense are very promising to shed light on some open questions in quantum field theory in curved spacetime. And with this, I thank you very much for your attention.
Thank you so much, Maxime. Let's thank Maxime for this talk. Unfortunately, you already ran a little bit of time. If there is one question from the, that's okay. If there's one question from the audience, okay, Morgan, try to be brief, please.
Okay, so I guess I won't even say a question. I'll just say I wasn't aware that you guys had a system where you can use an SLM to imprint on the essentially on the wavefront in a transverse sense. I think that these things are probably going to be a game changer. I mean, just as a simple example, you can make an airy beam with those things and make a self-accelerating polariton. I mean, you can basically any quantum field theory in 1+1 dimensions you can make by phase imprinting it with this thing.
Yep.
And that's I'll just leave it at that. That's a game changer. That's amazing.
Thank you very much for the comment. It's very nice to hear.
Yeah, it's really good.
Thanks.
That's great. Thank you so much, Morgan. Let's all thank Maxime again.